So at this point, we've introduced polar coordinates, but we haven't really highlighted why they're useful and what insight you can gain from them. So let's do an example of that, and I'll do an example that you've probably seen before in a Cartesian coordinate system, or actually you've probably seen results quoted, and then you've sort of pulled those results out relatively mindlessly when confronted with questions that required you to regurgitate those equations. So the example we'll look at first is uniform circular motion, and then we'll move on from uniform circular motion to non-uniform circular motion, and that'll probably be in a video after this because this will take longer. So you might remember in uniform circular motion that there's sort of the idea that, for example, you talk about the centripetal acceleration, right? And you're told that the centripetal acceleration is v squared over r. Right? Well, why is that? If you try to derive that, you certainly can derive that result in Cartesian coordinates, but it ends up being kind of a pain to derive it in Cartesian coordinates. And to the extent that we're talking about uniform circular motion, let's see if we can get some insight into what the nature of uniform circular motion is by, instead of using Cartesian coordinates, using polar coordinates and using some of the things we've seen about unit vectors. So how would we describe uniform circular motion in polar? Well, that's fairly easy to do. Uniform circular motion means that the distance from the origin is constant. So the magnitude of the vector is a constant r. And it also means that the angle increases or decreases linearly in time. So theta we'll say is omega times t, where omega is what we call the angular velocity. It's just a number in this case, and the units are some number of radians per second. So if we wanted to describe some object going in a circle, going around the circle once a second, then the angular velocity would be 2 pi radians per second, and so on. Okay, well, if this is the case, right, we can easily, using the stuff that we've already done about the unit vectors and the derivatives of unit vectors in polar coordinates, we can easily write down the position vector, right? It's just r times r hat, right? And note here that r hat is a function of time, right? If we want to find the velocity, that's pretty easy to do as well, right? So we take d by dt of the vector r, right? R is a function of time because r hat is a function of time, so it's d by dt of big R times r hat. Big R is not a function of time, but r hat is a function of time, so that's big R times d by dt of r hat, or r times theta dot times theta hat, or omega times r times theta hat. Now let's think about what that says. That says that for this definition of r and theta, the velocity at any given point, first of all, points in the theta hat direction. So the velocity points in this direction here. Later, when the object is up here, it points in this direction. It always points in the theta hat direction. And the size of the velocity is proportional to r and is also proportional to the angular velocity, right? It has the right units, right? R is number of radiuses. Omega is radiuses, is meters per radius times radius per second, so meters per second. And so omega times r could also be just talked about as the speed, right? V times theta hat. Finally, we can figure out what the acceleration is. It's the time derivative of the velocity, right? And the velocity is omega times r, so d by dt of omega times r times theta hat. And we know what the time derivative of theta hat is. It's minus theta dot r hat, so we get minus omega times r times theta dot times r hat, but theta dot is omega, so minus r times omega squared times r hat. Before we go any further, we'll note a couple of things about this. One is that it says that the acceleration at this point is pointing in what direction? Well, it's pointing in the negative r hat direction, right? So my acceleration is pointing in at this point. My acceleration is pointing in at this point, right? It's good old centrally directed centripetal acceleration. Right? These are my velocities up here. Oop, can't see that. Let's move that up there so you can see that. But we could also go further and say, well, wait a minute, we know what the speed is, right? The speed is omega times r, so I could rewrite this as v squared, right, divided by r. So it's minus v squared over r times r hat, right? So in other words, the question we asked, right, where does this v squared over r come from? Well, actually, all v squared over r is simply r times omega squared. So we've pretty easily shown a couple of things. One is that for uniform circular motion, acceleration is inwardly directed. And the second thing we've shown is the acceleration is given by v squared over r. Okay. Great, that's kind of cute, and it's certainly a whole lot easier than it would have been to derive it in Cartesian coordinates.